matrix algebra. So in this case, we're actually going to look at matrices. So we're actually going to be using, so rather than notationally using matrices like what we did in section 6.2, we'll actually use matrices to solve equations, systems of linear equations. So a matrix A is an array of numbers. It consists of, well, some numbers, a sub ij, for I going from 1 to m, and j going from 1 to n. I will usually denote in general as follows. And so this is a matrix whose ith, jth entry is a sub ij. And so this notation, the matrix with ijth element a sub ij, just means that, well, of entries A11, A12, A13, dot, 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 A1n, dot, 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 AM1, AM2, dot, 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 AMN, whose ith, jth entry, so looking at the ith row and the jth column, is a sub ij. So that is the shorthand notation for writing this matrix. Is just to say, well, it is a matrix whose ith, jth entry is a sub ij. M sub m cross n, or maybe with a comma, m comma n, is a set of all matrices with m rows and n columns, m by n. Equality of matrices. Matrix A is equal to matrix B if A sub ij is equal to B sub ij, and A is an m by n matrix, and if A is an m by n matrix, then B is also an m by n matrix, meaning that they are matrices of the same dimensions. So I can equate two matrices if they are the same dimensions and all of its entries are the same. Addition matrices. If A is an m by n matrix and B is also an m by n matrix, meaning they're two matrices of the same size, then I can add two matrices. The ith, jth entry in the sum will just be the sum of the ith and jth entry in each of those matrices. So it's just the matrix whose ith, jth entry is a sub ij plus b sub ij. Scalar multiplication. Suppose that C is some scalar, a number, and suppose that A is an m by n matrix. Then C times A is the m by n matrix whose ith, jth entry is C times a sub ij. Notation. A minus the matrix A minus the matrix B is just equal to A plus the scalar multiple -1 times B, times the matrix B. Of course, I'm assuming here that A and B have the same dimensions, so I can add them. 0, the 0 matrix is denoted by, well, 0 in matrix, and is defined by the matrix whose such that every element, such that the ith, jth element for every element in the matrix is 0. Let's do some examples. Page 588. Find a plus B. So in problem 13, A is equal to the matrix 2, 1, minus 1, 3, 2, negative 3, 2, 5. B is a matrix negative 3, 1, 2, negative 3, negative 2, negative 5. B will equal the matrix well, let's add 2 minus 3, negative 1. 1 plus 1, 2. 2 minus 1, 1. Negative 3, negative 3, negative 6, 0. 5 minus 5, 0. And so that is the sum of these two matrices. Find the additive inverse of each matrix. Well, will just be negative 1 times the matrix. So let's multiply each entry in this matrix by negative 1. So negative 3, positive 2/3, positive 5, negative 1/2. And that is your additive inverse. If you added these two matrices, you would find that you would get the 0 matrix, the additive identity. 17, find A minus B, where A, negative 3, 2, negative 2, negative 1, 4, negative 5, B, 3, negative 3, negative 2, negative 2, 5, negative 5. So let's subtract these. So A minus B is equal to, well, let's see. Let's subtract these. Negative 3 minus 3, negative 6. 2 minus a negative 3, 5. Negative 2 minus a negative 2, 0. Negative 1 minus a negative 2, same as 2 minus 1, 1. 4 minus 5, negative 1. Negative 5 minus a negative 5, 0. And so that is the difference of those two matrices. 5 times A. And so 5 times A is found by just multiplying each entry by 5. So 5 times 3, 15. 5 times 3/5, 3. 5 times 0, 0. Negative 5 times negative 1, negative 5. And that is your answer. Product of matrices. Let A be an M by L matrix. Let B be a L by N matrix. Then A times B is an M by N matrix. So notice that this dimension here, these dimensions for A and B are such that the number of columns of A is equal to the number of rows of B. Once you've done that, when you multiply the product, the answer will be the number of rows of A, the number of columns of B. Okay, so A times B is equal to the matrix whose ith, jth entry has the form sum k equal 1 to L, A sub ik times B sub kj. If we think of matrices as just representing linear transformation between vector spaces, then matrix multiplication is really just the composition of these functions, these linear transformations. Okay, so we can also think of it as basically a whole bunch of inner products that I'm doing. Find each product if possible. Problem 32. So notice I have the same number of columns here. It's the same number of rows. So good. So at the end, after I multiply this together, so I have here a 2x3 matrix times a 3x1 matrix. That should equal a 2x1 matrix. Okay. So let's do this. Oh. So let's multiply. 1, 2, -2, 0, -3, 1, 4, -5, -6. Okay. So let's see what this is equal to. So I want to multiply each element here by each element here. So I'll do, I guess I'll write this out long form. I'll do 1 times 4 plus -2 times -5 plus -3 times -6 Okay, so that gives me the entry in the first row and first column. Now let's find the entry in the second row, first column. So multiply 2 times 4, 0 times -5, 1 times -6. Okay. And so this is equal to 4 plus 10, 14 plus 18, 32. 8 plus 0 minus 6. 8 minus 6 is 2. And that is your answer. Okay. So you just basically find the dot product between this vector and this vector, between this vector and that vector. Okay, so that finishes off section 6.3. Let's go on to section